Ever stop to think about how a phone made in one country can use a charger made in another? Or how a car engine with parts from a dozen different factories just fits together perfectly? Well, it's not magic, not at all. It's actually a hidden language, a set of invisible rules that dictates how pretty much everything in our world is built. And today, we're going to dive in and learn how to speak it.
All right, so let me just kick things off with a question for you. Is anything ever made perfectly? I mean, like absolutely geometrically flawless? You might think the answer is simple, but trust me, it cracks open one of the biggest, most fascinating challenges in all of engineering.
Think about it like this. On one side, you have the ideal design. This is the perfect 3D model that lives in a computer, right? It has perfect lines, perfect circles, everything is flawless. But then you hit reality. The second you try to actually make that part in the real world, tiny, microscopic imperfections start creeping in. No physical object is ever truly perfect. So the real question is, how do you build a world that actually works when it's made out of all these imperfect pieces?
Well, the answer is you do it with a language. A very specific, universal language that isn't designed to get rid of imperfections, but to control them. It's called geometric dimensioning and tolerancing, but you'll almost always hear it called GD&T for short.
And this is where things get really interesting, because the core idea here is a total shift in thinking. GD&T is not about telling a machine, make this whole perfect. No way. It's about saying, okay, here's exactly how imperfect this whole is allowed to be. You're defining an acceptable zone of variation. It's not a quest for perfection, which is impossible anyway. It's all about the intelligent management of imperfection.
I mean, the research we're looking at today literally calls it a symbolic language that's used to describe imperfections. And that's exactly what it is. It's the only way a designer sitting in, say, Germany can talk to a manufacturer in Japan and have them both understand exactly the same thing, with absolutely zero room for misinterpretation.
So why does this matter so much? I mean, really, what's the big deal? Well, it's because GD&T is basically the secret engine that makes the entire global supply chain work, period. It's what lets a company design something here, build it over there, and assemble it somewhere else entirely, and still be confident that it's all going to fit. This language controls not just simple size, but complex things like the flatness of a surface or the precise location of a hole. Get that wrong, and oh boy, you are looking at a world of hurt, costly rework, wasted materials, and project delays that can cost a fortune.
Okay, so laying down the rules with these symbols is one thing. That's half the battle. But you also have to check the work, right? You have to measure the results. And that brings us to the next part of the story, the journey from a perfect digital idea to a real-world certified part.
And it works like a loop, this constant cycle. It starts when a designer specifies all the rules using GD&T. Then, of course, the part gets fabricated. But here's the critical part: inspection. You have to measure the real thing. And if it passes, it gets certified, confirming it does what it's supposed to do. This whole loop is built on our ability to measure things with just mind-boggling accuracy.
Which, brings up a pretty big question. We're talking about tiny, tiny variations here. So how in the world do you measure an error that's literally smaller than the width of a single human hair? You can't just pull out a ruler for that.
The answer is you use some seriously cool, high-tech gear. I mean, look at this. You've got things like X-ray CT scanners and advanced optical measurement systems, which make up most of what's used today. These tools are amazing. They basically create a perfect digital copy, a digital twin, of the real object so you can compare the physical part to that perfect blueprint, down to a single micron.
And it's only getting smarter. The next step is something researchers are calling, get ready for it, ontology-based intelligent certification schemes. Yeah, it's a mouthful, I know, but here's the simple way to think about it. We're basically teaching an AI to be a master quality inspector. The idea is to automate the whole process, making it way faster, more reliable, and not so dependent on having someone with 30 years of experience.
So this language of precision, it's not some old, dusty rulebook. It's alive. It's evolving all the time. Which begs the question, how is it adapting to the most cutting-edge, futuristic manufacturing tech that we have today? Well, one of the biggest new challenges is additive manufacturing. You know it as 3D printing. Because when you build something layer by tiny layer, you get completely new and unique types of geometric errors that you just don't see in traditional manufacturing.
And so, of course, engineers are rising to the challenge. They're writing brand new standards like ISO/ASTM 52902 just for 3D printed parts. They're pointing those advanced optical scanners at these new complex shapes, and they're even going back to something that sounds pretty simple: physical fitting kits. Basically, a go, no-go gauge to quickly test if a printed part is going to work in the real world.
But it's not all about the small stuff. The challenges are just as big, maybe even bigger when you go in the total opposite direction to projects that are just massive. I mean, almost unimaginably huge.
I want you to picture a tokamak fusion reactor. We're talking about thousands of enormous, ridiculously complex parts, and they all have to come together and align with near-perfect precision. You can't just ship them to the site and cross your fingers. The cost of just one piece being slightly off, it would be absolutely astronomical. So how do you solve a problem that big? The answer is something called virtual fitting. And honestly, this is where the tech gets really cool.
Okay, so instead of the old school way of hauling these giant pieces into place and hoping for the best, engineers do something incredible. They take a super high precision scan of every single real component after it's been made, capturing all of its unique tiny flaws. Then, they build the entire reactor in a computer. They run thousands of digital assembly simulations to find the one single, optimal way to fit every piece together. They solve the puzzle before anyone ever picks up a wrench.
So, all of this brings us to the big takeaway here: the future of fit. Because this language of precision, this whole concept of controlling imperfection, it is the invisible scaffolding that our entire modern world is built on. Think about it. GD&T is what makes everything possible, from the phone in your hand to those insane fusion reactors. And it's getting even more connected. New standards are creating a seamless digital link all the way from the initial design to the final inspection report, with no information getting lost. At the end of the day, understanding and mastering imperfection isn't just an engineering problem, it's the key to unlocking what we can build next.
And that leaves us with one last question to chew on. For the last century, we've been perfecting this language for humans to talk to machines. But as our machines get smarter, as AI gets more powerful, the next great frontier is pretty clear, isn't it? How do we teach them to speak the language of precision, all on their own?